Hello everybody, welcome into another lesson. So today we are going to be given circles and we're going to find the area of the shaded region. So yesterday we talked about areas of sectors of a circle. Well, what do you do in a situation where you don't even have a whole sector, you just have a part of a circle that's shaded? That's not even a whole sector. How would you find the area? Well, if we take a look at this circle here, circle O at the center, you have two radii of 4, and they form a right triangle, right? They form a right triangle here. Now, what do we know about a central angle and the measure of an arc of a circle? That they're equal to each other. So, this whole angle here, this whole measure of the arc, since the central angle is 90 degrees, the measure of this arc is 90 degrees. Okay, so we've established the measure of the arc. Now, what are we going to do to find the area of just this shaded portion? Well, it looks like really you would start first by finding the area of the whole sector. You're going to find the area of the sector first in this case. If we remember how to find the area of the sector, the area of the sector of the circle is what? That's going to be the measure of your arc, which is 90 degrees over 360 degrees times the formula for the area of the circle, which would be pi times your radius squared. Your radius is 4, so that'd be 4 squared. Well, what's 90 out of 360? That's 1/4. And then times 4 squared times pi, that'd be times 16 pi. So the area of the whole sector is 4 pi. Good news is we're going to leave everything in terms of pi and radicals again today. We're not going to do any decimals, so don't worry there. So we got one critical piece here. The area of this whole sector, if we were considering the whole sector, would be 4 pi. But we're not finding the area of the whole sector. It's really, if you look at this, it's the area of the sector minus the area of the triangle, right? Because the triangle's not shaded, so you have to subtract the area of the triangle. Well, let's go through and find the area of the triangle. This one should be easy. Since you have a right triangle, your base and your height are both even. They both stand up and lay down. So the formula for the area of the triangle, of course, is half the length of the base, which would be 4, times your height, which is also 4. Well, half of 4 is what? That's 2 times 4 is 8. So we found the area of the whole sector being 4 pi. The area of the triangle is 8. Now we just need to take the area of the sector minus the area of the triangle, and you'll get the area of the shaded region. So the area of the shaded region would equal the area of the sector, which is 4 pi, minus the area of the triangle, which is 8. So the answer you should get for the area of the shaded region is 4 pi minus 8. So that's how you do problems like that. I do have a few more. All right, let's do another one here. Yes, this will be a very small region. So we're just going to find the area of that really small sliver of the circle. Well, if you notice here, right, you have a circle with two radii of 3 that form a triangle. That's definitely an isosceles triangle. And you have here the measure of this arc is 60 degrees. Well, the measure of the arc and a central angle are congruent. So actually, this angle here at O is also 60 degrees. Let me write in a different color so it's easier to see. There we go. Okay. Well, we have definitely the base being 3, right? Of this triangle. Actually, first, let's talk about the area of the sector. I'm sorry, I jumped ahead of myself. Again, doesn't this shaded region look like the area of the sector minus the area of the triangle? So let's go ahead and find the area of the sector to begin with. So the area of the sector in this particular case is equal to the 60-degree arc, which is 60 degrees out of 360 degrees, times pi times your radius of 3 to the second power, which, what is 60 out of 360? That's 1/6 times 3 squared, that'd be 9 pi. So you have 1/6 times 9 pi for the area of the sector, which would end up giving you 3 pi over 2. So the area of the entire sector would be 3 pi over 2. Now we may move on to the area of our triangle. We don't know the height, but we know the base. Well, we have to draw an altitude, right? In order to get the height of the triangle, since this is an acute triangle. If you do that, you then form two right triangles where you have a 30, 60, 90 right triangle. So now, if the radius is 3, which is across from your 90-degree angle, in this case the hypotenuse is 3, right? And then the altitude comes halfway down on the triangle, because in an isosceles, or in this case an equilateral triangle, which is what you would get, the altitude splits the side it touches perfectly in half. So half of 3 here is 1.5. Well, 1.5 would be across from the 30-degree angle, so this leg is across from the 60-degree angle. What is 1.5? Times the square root of 3. That's what you would get. 1.5 times the square root of 3 would be the height, which actually 1.5 is also 3/2. So we can now do the area of the triangle, which of course is equal to half the length of the base, which would be 3, times half the length of the base times the height, which would be, in this case, 3/2 times the square root of 3, because that's what 1.5 is 3/2. So if we simplify this more, you would end up getting 3/2 times 3 times the square root of 3 over 2, which means the area of the triangle would be 9 times the square root of 3 all over 4. So now we know the area of the sector, 3 pi over 2. Then we know the area of the triangle would be 9 times the square root of 3 over 4. Now to find the area of the shaded red region, you just take the area of the sector, which would be 3 pi over 2, let me write this, area of shaded region that's going to be the area of the sector 3 pi over 2 minus the area of the triangle, which would be 9 times the square root of 3 over 4. And that would be the area of the shaded region, which looks like a mess, but it's 3 pi over 2 minus 9 times the square root of 3 divided by 4. So that one was definitely a fun one. Should just have a few more here. Think about 4 more is what I have. Oh, good one. This is going to be a big one here. Alright, we're going to find the area of the shaded region of this circle, shaded in red. It's most of it, excluding just a little sliver, right? Well, we know we have this arc here has a measure of what? 90. The whole diameter of the circle is 8. Let's really look at this here, okay? If this arc is 90, what does that mean? The rest of this would have to be 270 degrees, wouldn't it? Because 270 plus 90 is 360. So now we know the measure of the major arc. So let's go ahead and find let's go ahead and find the measure, the area of the 270 degree sector. So the area of the sector in this case is going to be what? That 270 degree arc out of 360 degrees times that pi times your radius squared. Well, if your diameter is 8, that means your radius is 4. Which is going to then give you, what's 270 out of 360? Well, that'd be 3/4. You'd have 3/4 times 4 to the second is 16, so this would be 3/4 times 16 pi, which when you simplify this, you would get 3 times 4 pi, it would be 12 pi. So the area of the 270 degree sector is 12 pi. But if we recall what 270 degrees looks like, it only covers so much of this. It would leave about this much still that's uncovered, right? 270 degrees would actually be this portion. This is the whole 90 sector. Well, what do we notice? the area of the shaded region is actually going to be the whole 270 sector plus the area of this triangle, in which you have the radius for your triangle. So now we can find the area of the triangle. Ultimately, the area of the whole sector, the area of this whole shaded region is going to be the area of the 270 sector plus the area of the triangle. So the area of the triangle is going to equal half that base, which is 4, times the height, which is also 4. Well, half of 4 is 2, times 4 is 8. So now we can find the area of the shaded region by simply adding the area of the 270 sector, which would be in this case 12 pi, plus the area of that right triangle, which is 8. So the area of the shaded region would end up being 12 pi plus 8, since you add the 270 sector plus the area of that right triangle. It almost just helps if you can visualize what you're really looking at here. That way you can know, hey, I have to add an area of a triangle to that 270 sector. All right, 3 more. Another good one. Anything else I'm missing? All right, so we have another area of a circle to find the area of, another shaded area. You have a radius of 6 in the circle. You have a 60-degree angle here. Well, okay, so what's one thing we notice? We have a 60-degree angle. What do we remember about an angle inscribed? Because this is an inscribed angle. If you have an inscribed angle in a semicircle, which this is, it's a right angle automatically. An inscribed angle in a semicircle is always a right angle. So now you actually have a 30, 60, 90 right triangle. So, if, okay, the radius is 6, right? The hypotenuse is your whole diameter. What would be the whole diameter of this triangle? That'd be 12, right? The whole diameter is 12. So, if the hypotenuse is 12, the side opposite the 30, which would be your base, is half the hypotenuse, right? That means your base would have a length of 6, and then your height, which is across the 60-degree angle, would be 6 times the square root of 3. So now we figured out the triangles. Let's do the area of the triangle first this time. It doesn't matter which order you start in, area of the sector or area of the triangle. Just know what you're looking at. Area of the triangle, of course, is half the length of the base, which would be 6, times the height, which is 6 times the square root of 3. Half of 6 is what? That's 3. Then times 6 times the square root of 3. That'd be 18 times the square root of 3. So we found the area of the triangle to be 18 times the square root of 3. Well, if you look at the shaded region, doesn't it look like the area of the whole semicircle minus the area of the triangle? Let's find the area of the whole sector next. The area of the sector is, of course, this is a 180-degree sector. So it's going to be 180 degrees out of 360 degrees times that pi times that radius of 6 to the second power, which 180 out of 360, that's 1/2. Then 6 to the second power is 36, so that'd be half of 36 pi, which would then give you what? 18 pi. So the area of the whole sector is 18 pi. The area of the triangle is 18 times the square root of 3. The shaded region is the area of the sector minus the area of the triangle. So to get the area of the shaded region, that's going to be equal to the area of the sector, which was 18 pi, minus the area of the triangle, which is 18 times the square root of 3, and therein lies your answer. The area of the shaded region is 18 pi minus 18 times the square root of 3. I got 2 more exercises, then we're done. Now these next 2 are very different. You're going to see how different in just a second. Yeah, I think you're beginning to see just how different this is. It almost looks like a pool ball. This kind of looks like a pool ball bit, doesn't it? These are actually really fun problems, in my opinion. All right. What else are we given? There's more to this also. Alright, so we have a shaded region in this circle where you have 4 sectors where 2 of them are 60 degrees, 2 of them are 120 degrees. How in heaven's name are we going to find the area of the sector? Well, you can almost picture this like a rectangle in a way. Start out with your rectangle approach and make some diagonals. So, what do we know about the diagonals of a rectangle? That they're congruent. And that they bisect each other. And then what do you get? What do you get next? This is probably the biggest question. So, you have here now you have you have four right triangles, right? You have four right triangles that are congruent to each other, then you have two sectors that are congruent to each other. That's how you're going to do this. We'll call this sector area 1. We'll call this sector area 2. We'll call this right triangle area 3. We'll call this one area 4. We'll call this right triangle area 5. We'll call this right triangle area 6. Now we have regions we can split this in and figure this out. So let's do our two sectors first. So area 1, of course, is equal to that 60-degree arc, because where these intersect, that forms a central angle of 60 degrees. So you'll take your 60 degrees out of 360 times, of course, your pi times, what is your radius, though? What would be the radius? Well, actually, we should probably turn to our right triangle first. I'm sorry for not doing that. But if this line here goes from the center where it reads a height of 2, that means this line here would have to be 1. So each of these here would have to have a length of 1 for your right triangle. Then obviously here we are forming a 90-degree angle here with the altitude. This central angle here would be ultimately 120, but since you have an altitude, it bisects into two 60-degree angles. This here would be a 30-degree angle, so would this, so would this, so would this. So now you have yourself a 30, 60, 90 right triangle. Well, to find the radius of such, the radius is actually the hypotenuse of each of these right triangles, isn't it? Since one is across in a 30-degree angle, the hypotenuse, the radius, is actually twice the length of the shorter leg, so the radius of this circle is actually 2. And I'll just write this all over so we have it. There we go. So the area of sector 1, area 1, your radius is 2. So you'll take that times 2 to the second power. What's 60 out of 360? 1/6 times, what's 2 to the second power? That's 4. That'd be times 4 pi. 4 pi over 6 would simplify into 2 pi over 3. So we found area 1, this sector. Well, it's obvious that area 2 is congruent to that. You have two congruent central angles and arcs across from each other, and vertical angles for that matter. So we can say that area 1 is congruent to area 2 by the area congruence postulate. So area 2 equals area 1, which would also equal 2 pi over 3. So now we found both of the sectors here. Now we need to find our four right triangles. So we have the length of one leg of the right triangle being 1. That'll actually be our height. But what is your base for each of these? What is your base? Well, the base is actually across from the 60-degree angle. We know that that's the square root of 3 times the shorter leg. So each base is actually the square root of 3. You have 4 congruent right triangles, so to find area 3, which is one of the right triangles, you'll take half the base, which would be half of the square root of 3, times the height, which is just 1, which would end up giving you what? Just the square root of 3 over 2. And then if you have 4 congruent right triangles, that means area 3 equals area 4 equals area 5 equals area 6, which would equal what? The square root of 3 over 2. Now that we know our 6 areas, all we have to do is add them together and we found the whole shaded region. So, to find the total area, that of course is just equal to area 1 plus area 2 plus area 3 plus area 4 plus area 5 plus area 6. Well, area 1 and 2 are both 2 pi over 3, so that'd be 2 pi over 3 plus 2 pi over 3. Now you have 4 areas, 3, 4, 5, and 6, that are the square root of 3 over 2. So you're going to add all these areas together and you're going to get a really cool number. So when you do that, the pi term simplifying to 4 pi over 3, plus now we add these like terms, the 4 square roots of 3 over 2, you would end up getting 4 times the square root of 3 over 2, which this will simplify further yet into 4 pi over 3 plus 2 times the square root of 3. So the area of that entire shaded region by adding the 6 sub-areas together is 4 pi over 3 plus 2 times the square root of 3. And I have one more problem just like this, then we're done. So, as I said, these are actually some really cool problems. All right. Got another pool ball example, which is actually kind of cool. These are really cool problems. All right. We're going to find the area of the shaded region. Each of these diameters, well, not the diameter, but yeah, actually it is kind of the diameter. Not the diameter, rather, I'm sorry, hold on. This whole side is 6, so is this whole side. We're even given that the height is 6. So we're going to find the area of the shaded region. Well, it's very similar to the last one. If you have the height of 6, and then you have the 2 bases that are 6, what do you really have here? You could think of this as a square, couldn't you? So you draw your endpoints here, you draw your diagonals of this imaginary square. Of course they intersect, but what else do we know about squares? That the diagonals are also in fact perpendicular. So the diagonals without this height of 6 form a 90-degree angle. The height bisects those 90-degree angles and the opposite sides. which means you actually have a 45, 45, 90 right triangle for each of these. So, if the whole base is 6 and it's bisected, that means each of these here is 3 for your right triangles. And then a 45, 45, 90 right triangle, the height again would be the same because it's a 45, 45, 90 right triangle. And then, of course, if this whole central angle is 90, if this is 90, well, that means these two central angles also have to be 90, right? So you're going to have 90-degree arcs on the opposite sides. Since the diagonals of a square are perpendicular to each other and congruent, you can now determine that you can now actually go ahead and figure out your arc measures. But one more thing here, we need to figure out the radius, which is the hypotenuse of the right triangle, right? That would actually be the radius since it goes from the center. Also the hypotenuse of a right triangle. What is the length of the hypotenuse of a 45, 45, 90 right triangle? It's the square root of 2 times one of the sides. So the square, it'd be 3 times the square root of 2 for your radius. And then like we did in the last one, you'll have two sectors, so you'll have area 1 and area 2. They'll be congruent to each other. Then you'll have 4 right triangles. Area 3, area 4, area 5, and area 6. So let's go ahead, let's start with area 1, which is a sector. Area 1 is going to be equal to, of course, your arc measure is 90, so that'd be 90 degrees out of 360 degrees times pi times what is the radius to the second power. That'd be 3 times the square root of 2 to the second power. Well, what's 90 out of 360? That's 1/4. That'd be times, what is 3 times the square root of 2 to the second power? That'd be 18. So you'd have 1/4 of 18 pi, which would turn into 9 pi over 2. So area 1 is 9 pi over 2 for this sector. Area 2 is a congruent sector, so we could say that area 1 equals area 2, which also equals 9 pi over 2. So we found the two sectors, now we need to find the area of the 4 right triangles. It doesn't matter which one we start with. Let's start with area 5 since it's kind of bigger. I didn't draw this proportionally correct, but they're all the same, believe me. Let's take area 5. Just one of the right triangles. The area, of course, is what? Half the base, which the base is 3, times the height, which is also 3. Well, 9 times 9, you'd have 9 halves. So the area of this right triangle is 9 halves. And then actually, the other 3 right triangles are congruent. So area 3 equals area 4 equals area 5 equals area 6, which makes them all 9 over 2. Now, of course, to find the total area, you just need to add your 6 areas together. So that's going to be equal to the sum of area 1 plus area 2 plus area 3 plus area 4 plus area 5 plus area 6. Then, of course, you just plug in those respective values. Area 1 is 9 pi over 2, plus another 9 pi over 2 for area 2, plus area 3 is going to be what? Just 9 over 2, and then you'll have plus 3 more 9 over 2s. and then you add your like terms here with the pi's, you would have 18 pi over 2 plus, all right, 9 plus 9 is 18, plus 9 is 27, plus 9 is 36 over 2. I almost forgot the pi on the 18. So 18 pi over 2 plus 36 over 2. Which in the end, this will turn into 9 pi plus 18. So the area of the shaded region with the 6 areas added together turns into 9 pi plus 18. So that's it for finding the area of shaded regions. We have one more lesson left in finding the area of 2D figures, which actually it's going to be in about similarity and ratios and proportions of areas with similar figures. After that, we go on to 3D shapes, where we'll get into surface area and volume and stuff like that. So I hope everyone has a great night. Take care.